Good day. For those of you who don't know me, my name is Douglas Harder, and in this topic we're going to discuss the inverse quadratic interpolation method. So in this topic, we will introduce the idea of using interpolating quadratics, and we will then discuss how to use this to approximate the inverse of a function. We'll describe how we can then use the approximation of the inverse to approximate the root. And actually, this results in a reasonably straightforward formula. We will then describe the rate of convergence of this formula, assuming that it is indeed converging towards the root. So following this topic, you now understand the inverse quadratic interpolation approach. And you know that this uses a quadratic interpolating polynomial to approximate the inverse of the function. You also understand that this approximation to the inverse is then evaluated at 0, which gives us our approximation of the root. And because it is a polynomial, evaluating at 0 simply results in the constant coefficient. You know that this method is order h to the mu, which converges almost as quickly again as Newton's method. Now let's suppose that f is a real valued function of a real variable. So y is equal to f at x. X and y are real. In this case, if x is a root, then of course f at x is equal to 0, obviously. However, suppose that f is locally invertible around the root, and therefore we can write x as a function of y in the vicinity of the root. So consequently, we can find a function f inverse of y equaling x. However, if this is the case, then f inverse of 0 must be a root of f. All right. So, for example, the inverse cosine of 0 is equal to pi by 2, and therefore cosine of pi by 2 is equal to 0. E to the 0 is equal to 1, and the exponential function is the inverse of the logarithmic function. So if e to the 0 is equal to 1, then ln of 1 must be 0. So 1 must be a root of the natural logarithm. Here's a nice one. If y is equal to 4x cubed plus 6x plus 1, then that function is 1-to-1 and onto for all real numbers. Therefore, there must be a unique inverse, and that inverse happens to be the function we write down here. Consequently, if we were to evaluate this at y is equal to 0, so substitute y everywhere within this expression, we get that a root of the original cubic polynomial must therefore be the cubed root of 2 over 2 minus 1 over the cubed root of 2. And you are welcome to substitute that value into the polynomial 4x cubed plus 6x plus 1, and you will see that this indeed does equal to 0. Now, I needed to use maple to get the inverse, and I needed maple to give me a cubic polynomial that was sufficiently simple that I could leave it on this page. So this is not normally how we would do this, but as an example, this shows yet again that this statement is true. Now, a function is locally invertible if it is locally 1-to-1 and onto. So here we see a function that is locally 1-to-1 and onto, and therefore, at least within the vicinity of this particular root, this function should be invertible. how could we approximate not the function, but its inverse? Well, actually, that's reasonably straightforward. Just find the polynomial that interpolates these points as opposed to the previous techniques we've seen where we had the x values first and then the y values, finding a function of x. Now, very important, the f values must be unique, otherwise, of course, the function is not locally invertible. So, once we find an approximation of the inverse, which is our interpolating quadratic polynomial, then all we have to do is to approximate the root is to evaluate this interpolating polynomial at 0. Wait a second. If we have an interpolating polynomial and we are evaluating it at 0, that means all we really need is the constant coefficient. All right. So here's the formula. It's a little messy, but it's something you can easily program into a computer. Notice that the difference of the f values are repeated so they can be calculated once and used over, including the differences. So here's our next approximation of the root, evaluating our approximation of the inverse at 0. Now, of course, this technique fails if any two of the f values are either the same or very similar. If they're the same, the denominator will be 0. If they are very similar, this technique is subject to subtractive cancellation. To ensure that the f values are likely to be different, this technique works actually quite well if the root is bracketed. So in this case, at least two of the differences of the f values are guaranteed to be relatively large, since the signs of two of the f values will be opposite. So this technique is not generally used as a standalone technique, but it will be used in our next algorithm, the Brentdecker method. Like Euler's method, if h is the error, then the rate of convergence of this function is order h to the mu, where mu is the real root of x cubed is equal to x squared plus x plus 1. And we can calculate that to be approximately 1.8393. Again, this is significantly better than the secant method. However, if we are bracketing the root, this is even better than either the bisection method or the bracketed secant methods. So following this topic, you now understand the inverse quadratic interpolation approach. And you know that this uses a quadratic interpolating polynomial to approximate the inverse of the function. You also understand that this approximation to the inverse is then evaluated at 0, which gives us our approximation of the root. And because it is a polynomial, evaluating at 0 simply results in the constant coefficient. You know that this method is order h to the mu, which converges almost as quickly again as Newton's method. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!